S.201.
Hey everyone, just getting started pretty quickly here. It is second office hours of the day. We'll start doing some of the assignment here. Anyone in the chat? Do we have anyone watching? Let's see, 2 people watching. Says someone's watching other than me. If you are in the chat, feel free to say hi. Hey Nancy, Brooks, Sawyer, good to see you there. Mubot can see you now. Yes. I'm getting my own emails now. Let's start here. Should we do the homework first or should we do the quiz? You tell me. My hair's all crazy. Homework or quiz? What do you say? Homework or quiz? Homework. Let's do that full homework. Do the full homework. Jordan, everyone wants the homework. You got it. Could you do the CEO question? Yeah, is that on the quiz? I think, Macy, is that only on the quiz or is it the homework to start? Because I know you emailed about that one. Really good question. Sampling distributions. It's on the homework? Let's do it. We might do all of it in order. We will do all of it. Some will be quicker than others. Let's do the full homework starting now. Okay, this is the full entire homework. Let's just get it done, then do some of the quiz. Probably can't do the full quiz, but here we are on the full homework. So this is Stat 201, Chapter 14, Homework. Question 1. Okay, when you get to the test, you need to mark your what? When you get to the test, I was doing it here. You need to mark your what? You get to the test, you get to any problem, do this when doing the homework, you get to a question, you mark your what? You got to know to do this.
Notation.
What do you got to mark? What do you mark? What do you mark? What am I going to... I'm marking my what? Mean standard deviation, you got to mark that.
Notation,
brother. You got to mark all the notation. So you got it right there, Nancy. Great work. This is the actual weight of the salmon. Like from what we know, the weight of the salmon is on average 26 with a standard deviation of 2. That is sigma equals 2. These are different sample sizes, like the sample size for a box, a sample size for a carton, and a sample size for a pallet. So those are different sample sizes respective to the different groups. And then it wants to know the standard deviation. So the standard deviation of y bar is sigma what? It's not just sigma. The standard deviation of y bar is what? Sigma what? What is it? And then you go to the formula sheet, especially if you're doing a test, because the formula sheet, we'll put review 3 on here. What is the standard deviation of y bar? Square root of n, call it on fire right there. I like it. Points in the chat. So square root, let's make this go crazy right here. Square root of n. And so especially look at the formula sheet. You want to go and print this off. You want to know how it works. That when you're trying to get, that's test 3. Ooh, don't go there. That's test 3. Don't test 3 yet. We want test 2. I did review 3. You both sent us to the wrong spot. Review 2 is where to go. And we go here to the formula sheet. And we're right down here across the bottom row. We're looking at the standard deviation of y bar right there, which is going to be sigma over the square root of n. Very important you know that. Sigma over square root of n, know how to find it. And so all we do is take the original standard deviation of 2 and divide it by the square root of 4, which is 2 over 2. The next one is just going to increase to the larger sample size. So it's going to be sigma over square root, and this was the box. It's then going to go up to the carton. So this is over n carton. For the equation sheet, could I write it out? You can write it out in different colors, and then you can't add extra notes to it. That's a large and then a lowercase n. You can't add extra notes to it. Just make sure it's just the formula sheet, and you can use that. So the next question, when we keep working through this, is going to ask for the bigger size, which is going to be over the square root of 36. And you notice here that the standard deviation is constantly getting water as n increases. This new standard deviation quantity, which is the standard deviation for the distribution, is getting water as n gets larger. This quantity over here at the end of this is getting smaller. And it also gets tighter. Yep, that means it's getting smaller. So the next one right here, I get one off the screen a little bit, is going to be, I only have a little more room to write, so sigma over square root of n is equal to, and this is for the pallets, This is going to be 2 over square root of 100, which is 2 over 10. And those are all the answers right there. So we simply plug them in. The first one was 1, check answer right. The next one was 0.33, check answer correct right there. Next answer was 0.2. Once again, we just solved out all the work over here because I knew what the questions would be. And we just solve out all the work for each sample size respectively. And so we're seeing that which one would be the most normal is going to be the largest sample size because, as Nancy said right there, it gets tighter and more normal by a factor of the square root of n. And this is the two things of the central limit theorem. The central limit theorem states that if you have a large enough sample size, you could take a distribution that is skewed. And if you get a very large sample size, like something like 25 for a skewed distribution, well, these samples, this is the distribution of sample means of size 25, are going to build up into a normal distribution. But if n is not large enough, like you only have an n of 2, key points of the quiz, yeah, Juliana, I'll do that after this homework. Stay tuned. It might be like 20 minutes or so. But Juliana, really good question. Let me throw some points. We'll do some quiz stuff. Do you think gas attending Disney parks is decent enough distribution size? Oh, yeah. That's a large enough sample size right there. Colin, good to see you in the chat. Let's throw some 5,000 points for Colin at Disney in the chat. I think that's a big enough sample size. And the larger the sample size is that we take from a population, like from a day of Disney visitors, that distribution on the amount of money they spent is probably going to be normally distributed for the average amount of money spent daily at Disney. I like that right there. So for the larger sample sizes, it wouldn't really even matter for the underlying distribution because the palettes is a very large sample size and it would meet the large enough n criteria. Let's keep going to the next question right here. So once we finish off this homework, we'll do that. Then we'll do 320. Then we'll do quiz. So here we are with 10. Thank you so much, Juliana. I want 320 in here. Perfect time to ask. Sample size. Oops, mistype. Thank you so much, Colin. And so you make me smile, Colin. I really mean that. Like, I love seeing you in the chat. I tell students all the time about Colin working at Disney, and you are just an awesome individual. A standardized test for graduate school admission has a mean of 150 and a standard deviation of 8. The distribution is unimodal symmetric. A test preparation organization tests a small class, 9 students, and a larger class, 36. What do we need to mark for any question? Say it with me. We need to mark our what? Do this for every question. See if you can do it before I do it, but you got to know what you need to do. For every question, you have to know your what. Because that's a lot of these comes down, especially at the end of the semester, and comes down to knowing your what.
Notation.
What do you got to know for this one? See if you can do it. Does anyone know anything on here? Anything. Notation, brother. So what are any of these? What's any of these? Colin, good work right there. What's any of these values? Well, it says they have a mean, and this is like according to the full testing data. It is the mean, but what kind of mean? What kind of mean? What kind of mean is it? Is it a this? Is it a this? Is it a this? Is it a this? Which one is this? It's technically 2 of them. Which one of those is it? It says a standardized test for graduate school has a mean of this. Has a mean of this. This is the mean of it. It is actually in Jackson. Good guess right there. This is mu, which mu y bar equals mu. So it would actually be the expected mean. It is mu. How about the next one? Standard deviation. Well, there's S d y bar, there's sigma, there's S, there's p hat or p times q over n square root, there's sigma over square root of n. What is, it has a standard deviation of this. It's just saying this is its standard deviation of all the data. Which one of these is it? Which one of these is it? It's saying this has a standard deviation of this. Like all the data has a standard deviation of this. So which one is it? Don't worry about being wrong. This is practice. Which one of these is it? Don't worry if you're wrong. I like for someone to take at least a guess, and I'll give the answer away. Good guess, Nancy. P and Q, this is literally just sigma. So that value right there is just the standard deviation. Sigma is the standard deviation of a population. So that is just sigma. There is no P and Q for this problem, so I was being tricky. P is the true proportion. Q is the complement of the true proportion. P times Q over n square root is the standard deviation for the distribution of the sample proportion. This question has no P and Q, though, because it's not a categorical question. We're looking at scores on a test. And this would be sample size of the large group. And this would be sample size of the smaller group. I'm doing just a subscript right there. And this is the shape of the distribution, which could be used for the large enough n. So that is, you could replicate this question in different ways, but that's the underlying information and knowing your notation, which is very important for the test. Okay. What would you expect the distribution of the mean for the class scores to be? Well, here's the equation. Mu y bar equals mu. So they should both have different means. One should have a larger mean, a smaller mean. Well, if you do it for the small class, you would say mu y bar equals mu, which is 150. So if you do it for the small class, so what would be the mean for the larger class? If you do mu of the y bar for the larger class, it would equal to what? So solve the, what was it going to equal? Mu y bar of the larger class, the expected mean for the larger class is what? You just solve the equation. You just go right here and you say, oh, I have to go here and solve the equation. Well, it's mu y bar for the larger class equals what? For the smaller class, mu y bar equals mu, and it's 150. So for the larger class, mu y bar equals what? What does this solve out to? The larger class has a mu y bar of what? So we just have to plug in mu right there. So what's the answer? Review the formula sheet we went over today in Office Hours Jackson. Really good question. Try to come up with examples. So this is the expected score of the larger class on average would be what? Yeah, Colin, you guys, just 150. Yeah, because it's mu. And so what does this mean? The sample size has no impact on the mean. So both distributions will be approximately normal with a mean of 150 because the mean doesn't change. So now we get into the tougher parts. Now we get into this part of the question, which says there are certain means. I mean, there are certain observations. So now this part of the question says, we saw for both classes, the average of class 1, which is the small class, hypothetically could be 158. The average for the large class could be 158. Which of these is more weird? Well, with that, we need to come up with a z-score. The z-score is going to be z of y bar is equal to the observation, what we see in the sample, minus the mean over the standard deviation. And the standard deviation is specifically sigma over square root of n. So we plug in the numbers right here. So for the smaller class, it's going to be 158. We'll write a small next to that over there. We'll put a divider and put a large over here. 158 minus 150 over, we have to take sigma, which sigma is 8, divided by square root of 3. We can solve that out. The larger class is going to be 158. The only thing that's going to change is the sample size here. 158 divided minus 150 over 8 divided by square root of, oh, did I put 3 on the bottom of that? Why did I do that? Okay, so I was already square rooting it. 9, and this is 36. The sample size respectively, remember, the small class is 9, and the large class is 36. And that's what's going down there on the bottom. Is everyone following this right here? Do people understand the equations I've written? Like why I've written, I'm using this formula and plugging in the values down there on the bottom. So I'm just plugging in the observation we observe in the class of 158. Observation minus the mean of 150, stated up there, over sigma over square root of n. Sigma square root of n. The only thing difference between these formulas is the n's. And so we run the equation right here. And for the first class, we get 8 divided by 8 times 3. Should be right. Should be 3. I believe it is. Let's see right here. Yeah, I think it is. That looks right. So it's 3. And then over on this side over here for this equation, This is 8 over 6. When you divide it out, 8 over 6, which is 1.33. So 8 divided by 1.33. So it should be, that sounds about right, 3 and 6. These are the z-scores respectively. Put them in your calculator, double check your work. And there's the z-scores. So the small class is less unusual because their z-score is smaller. So for the small class, z-score of 3. For the large class, z-score of 6. And it's more likely for the small class to have this because they have a less unusual z-score right there. And now we just take 146. And if you think about this, can anyone logic this for me? We can logically solve this one. Try this real quick. You ready? Who's with me? Type a Y in the chat if you're listening to me right now, because I bet you can logic with this with me. Type a Y in the chat if you're with me right now. Just a Y, just a singular Y. Okay, Jackson's with me. Anyone else? Ashlyn's with me. Nancy's with me. The z-score for 158 was 3, meaning this is 3 standard deviations above the mean. Does everyone understand that? That 158 is 3 standard deviations above 150. Who's with me on that? Type another Y if you understand that. Like, oh, we figured out just a moment ago that 158 was 3 standard deviations above. Okay? So 8 is 3 standard deviations above 150. This is how far below 150. This is, just tell me, this is how far below 150. 146 is how far below 150. I think Jackson, well, so 150 and 146 have a difference of what? Because this is 8 above. 158 is 8 above 150. 146 is how far below 150. Just mathematically. How far away is 146 from 150? 4. Does anyone already know what the z-score is here? Think it's half the distance. 3 standard deviations is a distance of 8. So if it's half the distance, its z-score should be what? And we can, I'll show the math on this in a moment. I'll write the formula. But just think logically, like, oh, if that one's 8 above and this one's 4 below, and that one's 3 z-scores above, this one should be how many below? Let's see if anyone gets it. And I'll show it. Because it's half the distance, so its z-score should logically be what? If it's half the distance of there, Jackson, 5,000 points. Yep, it's half the z-score. You can just half both the z-scores, and the small class is still less unusual. We can check our work, and we got it. Just to show you how that would be done, all you would do is go in here, and they want you to put in a positive number. All you would do is just change this number to 146. And then you would math this out. Do people think they understand this? Like, you would just change the observation. All we're changing is the observation for that question. And you just change what you observe and saying, would this be an unusual occurrence? Will it be at 1.5 below or -3 below? And the distance changed up top. It was 4 now, and it was 8 previously. I think Jackson sees it, but we were able to logic that one out because it was half the distance. And so if it's half the distance, it's half the z-score, because z-scores are just the distance standardized. Okay, just 146 minus 150 divided by the standard deviation. Observation minus mean over standard deviation. Standard deviation, bigger one. Yeah, exactly, Jackson. That's the thing. And it really just comes with practice. Like, you have to be able to read the questions and solve the equations. I cannot state enough how much, like,
Notation.
it's all about notation. Like, be able to come up with example problems here. Let's look at this one. Question 4. Yeah, we're going to be doing that here in a second. Grace, you got it. We're rocking and rolling. We're going to get the full thing done, and I'm marking each one. So if anyone has to go, please stay if you can. But if you have to go, we will have it. You're welcome, Grace. How about this one? A waiter believes that their tips are slightly skewed to the right with a mean of this and standard deviation of this. Okay, so what's the notation? You ready to practice? They believe, they think it's true. So what is this value right here? And what is this value? What are those values? We should mark our notation. Is that y bar? Is it y? Is it mu? Is it mu y bar? Is it y hat? Is it p hat? Is it p? Is it q? What is that value? So this is quantitative. This is the way to know it. We're talking about quantitative. So if you're trying to figure out which one it is, has nothing to do with those because that's not quantitative. So it can't be P and Q. It can't be any of that. It's quantitative. It's how much do you get tipped. And we're saying this is like what they believe is true. Kind of, Jackson. I'll give you some points for that. Kind of. It is mu y bar because it is mu. So the reason it is mu y bar is because mu y bar equals mu. So in technicality, you're right. So it is, in very technical sense, it's the true mean, but the true mean is the expected sample mean. So if we took a sample of their tips, we'd expect to see on average that. So what is standard deviation? And it's for all the tips. Is that S? Is that sigma? Is that SDY bar? Now this one you got to watch out on. Which one is that? Standard deviation is what? These questions aren't even asking us this, but we got to know it. Which one is it? Don't worry if you're wrong. Just take a guess. It is sigma, Jackson. Right there, you got it. And this one is not the same as SDY bar because SDY bar is equal to the equation of sigma over square root of n. So these two are not equal among each other. You can't just say, oh, it's SDY bar, because it's not the standard deviation of the sample mean. It is the true standard deviation. And notice how mu and sigma go together up here because they are the mean and the standard deviation of a distribution. Explain why you cannot determine what if a party will tip in $20, the probability of this. This deals with the large enough n. Because if you have a skewed distribution and you're only looking at a party, your sample size is not what enough. If you have a skewed distribution and you're only looking at a party, your sample size is not what enough. This is the large enough n condition. Because that's the distribution of one sample. It's not large enough. Jackson, would 2 be large enough? If we started to do the distribution of means of sample size 2, is 2 a large enough n for a skewed distribution such that the distribution will be nearly normal? You check the conditions, the 3 conditions, random, 10%, and large enough n, to understand if the underlying or the parent, to understand if the sampling distribution will be nearly normal. The shape of the original distribution is stated to be skewed to the right. And now we're checking for a sample size of 2. Is that large enough? Well, you can see the answer down below. The answer is yes or no. What is it? Is 2 large enough such that the new distribution of the mean will be nearly normal? That's the answer. No, it's not large enough. What we'd hope is at least 25. Now, this question is going to play games with us. It's an all right question, but let's see what they say. So the distribution of one tip would still be skewed, meaning it's not symmetric. And let's see here, $20 is greater than, no, it'd be, the distribution is skewed, so meaning it's not symmetric. We would need larger sample sizes. I think that's right. Don't love the way it's stated. Can you do it for 4 parties? No, 4 parties is not large enough, so the central limit theorem will come into play. Let's see. No, using sample size of 4, have more, no, here it is. It doesn't. The answer just got into nonsense right here. I was like, no, not right. A sample size of 4 parties is probably not large enough. And literally, they're talking about the large enough n condition right here. 10, and this is where 1, 25, and 100, Jackson got 3 some more points. Those are the numbers we like to use. Some people are more forgiving. It's going to be more normal the larger n is. So while the sample size of 10 may not be large enough to use the normal model, it is likely that it will become more normal. And what will be the standard deviation of it? The standard deviation will be the A or B. Which one will be the standard deviation? Is it A or B? It's actually A. I'll throw you some points, Jackson. It's actually A, because the standard deviation of the distribution will be the original standard deviation of 5.40 divided by the square root of 10, which is like 3.1 or so. That was close enough, apparently. I got, it's gonna be a little bigger. Square root of 10 is 3.16. So it'll be 5.4 divided by, 5.40 divided by square root of 10. And there's right there, 1.71. Exactly, sigma over square root of n. And that's what answer A acknowledges, is that the new standard deviation, and they even calculate the z-score on it, the new standard deviation. The waiter-waitress question. Dun, dun, dun.
It doesn't matter.
Got all the
Wow.
things. It is the waiter waitress question, the question of all questions of questions. Where's my notes? The waiter waitress question. One of my favorite questions. I've done it a lot. The waiter waitress question. They change it between waiter and waitress when you're doing it. Are we going to get credit for the bonus normal curve? Yes, I need to add that in. Sometimes it takes till a little bit later in the semester for me to add those. Thank you so much, Nancy, right there. I will be adding that on. I'll be adding that on probably to your guys' quizzes. Thank you so much, Nancy. Good question right there. I do see it, and I haven't used it yet. So hopefully I will have some time coming up here, especially with spring recess. It's getting everything organized. But thank you for doing it. And I'll be taking a look who did some of the really awesome drawings right there. Okay, because the normal curve is very important. This question is going to actually use the normal curve. So what do we do to start the question? How do we start the question? What do we do? Any thoughts on what we should do to start this out? Does Leo have advice?
Notation, brother.
Anyone got advice for this question? Any advice? Bueller? Identify variables in notation. Is this a quantitative or categorical question? We're asking tips. Is this quantitative or categorical? Notation, brother. It's quantitative. Great job, Grace. Right there. It's quantitative, which means we're going to use equations like mu y bar equals mu. And so we'll have to find that. Does anyone know any of the notation for this? Great job, Ashlyn and Sawyer. Sorry, taking those points. And then S d y bar equals sigma over square root of n. Okay, so what's any of the notation? Any of the notation. Help me out right here. I've got them highlighted. What's any of the notation? This was tricky. Fall asleep. We have 30. We have 30 parties she waited on. Her average tip, she knows, and we have a shape of a distribution right here, slightly skewed to the right, which means our sample size is large enough because the requirement is, Jackson was saying a moment ago, is 25 and needs to be larger than. We also see the n on there. Any of the notation? Any of the notation? I don't want people getting confused about that 25. We're talking about large enough n right there. Any notation? Great job, Jackson. Yeah, Jackson's got some stuff right there. I think you got it all correct, Jackson. This is going to be the mean. This is going to be the standard deviation. This is going to be the sample size. And this is the sum of y. Meaning if we divide the sum of y by n, we can actually get y bar. So think about this. If I take if you're like, what does that mean? You have 3 people in a room. Person 1 can do 8 push-ups. Person 2 can do 10. Person 3 can do 12. So what is y bar? What is y bar? What is the average amount of push-ups people can do right there? What is the average amount? Just look at this and tell me what is y bar for this data. It is 10. Well, to do that, you would need to take the sum of the observations. You take the sum of y, which is 30, and divide that by 3, and there it is. Does that make sense? So it's saying her total tips are 300. So what is the average y she wants to make? Because she wants to make $300 on 30 parties. So what is her average tip she wants to make? To make $300 on 30 parties, you would have to average what? To make $300 on 30 parties, you'd have to average what? You need to average how much money? Like, man, I want to make $300 this weekend. I got 30 parties. Great job, Grace, right there. Yeah, that's the total over how many? That's right, Jackson. And then Grace has the calculation of 300 divided by 30. She will need to average $10. So that is how much she needs to average per table. $10 is what she needs to average. So now what we need to do is we need to find the mean of the distribution. Okay, so what's the mean of the distribution? I'll highlight in green what I'm talking about. What is the mean of the distribution going to be? What is the mean going to be? Anyone know what the mean is going to be? What is the mean of this distribution? What would she expect to make? It's mu y bar equals mu. And we know what mu is. Oh, fall asleep. So what should she expect to make? Well, that's what she wants to make. She wants to make $10, but she usually makes $9.20. She's like, man, I want to make $10 on every table on average. But I usually make on average. And think about this. If she usually makes $9.20, excuse me, then she would expect to make $9.20 if that's how much she usually gets. What's the standard deviation? So what's the standard? Try to solve the standard deviation. We're almost done. It's downhill once we get this. Like we'll be rocking and rolling. So once we need to get the standard deviation. What's that going to be? Who has it in the chat? I can get it and I can show you, but be careful. Remember, we're getting the new standard deviation. I want to make that clear. We're getting the new standard deviation. I'm trying to estimate in my head right now, okay? I got an estimate. I have an estimate. Can I take a guess at this? It's gonna be very high probability. This is a very hard one to guess today. What's the new standard deviation? Well, we plug in the numbers. 5.40 over 30 and square root that. And then we plug in, it's gonna be about 1 or so, a little bit bigger than 1. No, maybe about 1. 30 square root. Wait, what? Is that really right? Square root. Wait. 30 square root. Okay, good. 5.40 divide by. I'm getting this right here. Does everyone see what I did? Yep. I think Sawyer's got it. Yep. So 0.9859. Carry all decimals till the end. And then here's what we do to solve this. Is we go to the app. We go to the app, which is pinned by MuBot right now. And this problem gets way easier. We put in the standard deviation. And so here is the standard deviation. Boom. We put in the mean of 9.20. And then we go and solve for the probability above x, which is 10. And there's the answer. And then we do 4 decimals. And we now have done it. There is the answer. There's the probability she makes above $10 on a curve that has a mean of this and standard deviation of this. And then we did above 10. How are we doing? I did the last few things really quickly. I just plugged in the mean. I plugged in the standard deviation. And I found the probability of greater than 10. Because it says what's the probability she makes more than this, which means above it. How are we doing on that? So that's got it. We just take the value right there and plug it in. And how do you find it without the applet? It'd be a lot tougher. You could draw it out. We'd have to change the way the question's worded. Like on the test, what it could ask you is it could ask you the z-score. So if the test said find the z-score, what would you do here? The test could easily ask you the z-score. So what would you do if it said find the z-score of 10? What would you do here if it said find the z-score of 10? So Jackson, really good question. The test could say, what is the z-score of it? So what would you do? Well, that is equal to observation minus mean over standard deviation. And so you'd have to plug in right here the values. You take the observation minus the mean over the standard deviation, which we solved of 0.9859. And you'd go right here. And you do 10 minus 9.20 divided by this. And you get a z-score of 0.811. And if you were to do the z-score, you could go to the applet 2, which is not bad to solve it using the z-score. On the applet, you'd enter in 0 and 1 and do 0.8211, and there's the same value, 20.58. So there it is. Or did I not enter enough decimals? 114. I might have not carried enough decimals. It might have accepted that. Just make sure you enter in enough decimals and everything. For mine, the correct answer was this. It could be. It could be. Yep. All depends. You sound like you landed near the middle of the curve. Make sure, Nancy, you're using the new standard deviation. Don't use the old one. If you're doing the applet, you need to enter in the new standard deviation. Notice that that is not the original standard deviation up there, which I apparently 0.98 or so. It needs to be the new standard deviation that we solved for, not the original one. Very important. You use the new standard deviation. And then the total amount she earns on the best 1% of weekends. Well, I need to recalculate my standard deviation because I lost it. So 30 square root, and then 5.40 divided by, and then we go back here and we drop it back in. Now, here's what we can do. We can find the best percent of weekends by going over here and doing this. Now, what does this value mean? Remember, she waited on 30 tables. This is her what tip at 30 tables. This is her what tip. On 30 tables, this is her what tip. And this is the best 1% of weekends. Because this is the distribution of, think of an M word. We're looking at the distributions of what's. So this is her what tip. This is her average tip. Well, but that's not how much she made on the best weekends, right, Jackson? This is what she averaged. So what should we do with this value right here if this is her average on a weekend where she waited on 30 tables? If that's her average tip, like how much she made on average on tables, and she waited on 30 tables, what should we do? So that was her average for 30 tables. Like, oh, I averaged $11.50 this weekend on my tables. So what should we do with it? What should we do? I'm thinking. Yeah, Jackson, you got it. Because, yeah, there you go. You times it by 30 because that's how much she averaged. Because we're talking about a distribution of means, not the singular distributions. And the 2 decimals right here. It should have a little give on it. There we go. Yep, that's the waiter waitress question. Might have some easy ones now, but that one is tricky. It just requires a lot of steps, a lot of notation. Know the steps, know the notation, and you can do it. You too can solve the waiter waitress question. Okay, let's get the last few ones done right here. Okay. Which of the following conditions is not checked? Condition 1 is what? What is condition 1 for chapter 13, 14 until the end of class? Not chapter 7 and 8, which are QQ straight enough, no outliers, plot doesn't thicken. What's condition 1 for the remainder of the semester? Random. Got to random select that data. Condition 2 is less than 10% of the population is sampled. And what condition do we check for this chapter? This chapter, we're going to be checking the what condition. I know it's not the answer to the question. I want to know which one are we doing this chapter. This chapter, we are doing the what condition, the large enough n condition, which deals with normality, called the large enough n condition. So it would be, they're kind of saying it right here. I hate that they phrase it that way. It's called large enough n. We're not doing success failure, which is categorical data, chapter 13. This one, here we go. Let's do it. This one is a very good job, Nancy, right there. And this one is a very mathy one. Here we go. Okay. No, deleting. Okay. So for this one, the first part of it is very easy because they're saying theoretically, what would be the mean of the distribution? The formula for the mean of the sampling distribution of the mean, or expected sample mean, is equal to mu. That is the answer to all of these. Notice sample size is changing, but here's a test question. As sample size increases, the mean of the sampling distribution will do what? As sample size increases, the mean of the sampling distribution will do what? Look at the math over here for the answer. Notice, sample size is n. Jackson, you got it right there. It stays the same. So you know what the answer to all of these are? Rock knows. It doesn't matter. Doesn't matter. Doesn't matter what the sample size is. The mean will stay the same. So it'll be 10, 5, there we go, 1, 3, 8. Copy, paste, paste, paste. Same answer each time. Now the standard deviation is going to get water. The standard deviation, if we look at that equation, is going to get water. If we look at the simulation, we'll see that. The standard deviation is going to get small. Jackson, you cracked me up, man. I like it. Some points in the chapter, Jackson, everyone. Is going to get smaller. And that's because the standard deviation of y bar, my gosh, standard deviation of y bar is sigma over square root of n. And that's what this quantity is right here. It's talking about this is this quantity. It's not the same sigma. Sigma is that. That's what sigma is equal to. This is sigma. And then n are these. So all we're going to do is take 19045.52, and we will just do this repeatedly and change the what. Each time we solve, we're going to be changing the what. Every time we do this, we're just going to rerun it by changing the what. We're going to rerun it by changing the what every time. Each time we have to resolve this, we have to change what. Because sigma's not going to change. Sigma is what sigma is. Every time we do it, we're just going to change what the value of what is. Just think what's highlighted here. We have to change the value of n. And so let's be careful right here. So we've got 30 square root. Sample size, how many we sample. And just copy paste in 2 decimals, and then you just take the next one and do 50 square root. Now, why is 100 going to be easier? Why is 100 going to be easier? Oh my gosh, no. Why'd I do that? 19045. There we go. 100 is easy because I can actually solve it in my head. Exactly. Square root of, because it's 10, right? Next one's divided by 14, which I can't do. The square root of 200 is like 14.14. There it is right there. It's a neat number. I've done that one so many times. I've seen it. Now, when you... that's calc errors. Calculator errors. Make sure the numbers get smaller, and they should kind of replicate the numbers over here. Not exactly. The simulation will be close to, not perfectly, but there we go. That's got it. Yeah. Oh, Nancy, so glad. Nancy, 1,000 points. Good job. The theoretical means are close to, reasonably close, and they're reasonably close because the simulation models reality. Yeah, so simulation models... It's literally, you're just doing the central limit theorem applet. You're just doing this right here. Like, try this. What will... Yes. Oh, perfect. What will the... No, I actually want something different. Yes. Okay. What will... I want more built up there. What will the new mean of this distribution be? What will the new mean of this distribution be? Perfect. What will the new mean of this distribution be? When I run the simulation down below, what will the new mean be? Mu y bar equals mu. This is mu. So what will be the mu y bar down here on the bottom? The mu y bar, if I keep running the simulation, will be what? Who knows? This is mu y bar down here. This is mu y bar. This is mu. Mu y bar will equal mu. It's going to be the same because remember the mean doesn't change. Mu y bar equals mu. If sample size is larger, for the distribution of the sample mean, it doesn't change. So when I run this simulation, this will become 13.39. I'm going to run more large n right here, the large enough trials. But what will the new standard deviation be? The standard deviation is 10, and I'm taking samples of size 25. So the new standard deviation will be what? So the original standard deviation is 10, and I'm taking a sample of size 25. So the new standard deviation will be equal to what? What will it be? Well, the original standard deviation is 10. That's sigma. So here's sigma. And then will be the new. Will be smaller, but how small? What's the equation, Jackson? Isn't it sigma over something? So Nancy, you're on the right track. You're thinking of square root of n, but it's sigma over square root of n. So since it's sigma over square root of n, here's sigma. So when we run the simulation, it won't be 5, which is square root of n. You take 10, divide by 5, and you get 2. Sigma over square root of n. Yeah, Jackson, I like it right there. So do you see this is 25? And you see it looks kind of normal now because it gets more normal and tighter by a factor of square root of n when it gets tighter. So this is sigma. Sigma's right here. This is sigma, the original standard deviation of the parent population, the original full data set. And then this is the new standard deviation for the distribution of the sample means of sample size 25. Nancy Jackson, do you get it? Is it like, does it make sense? Like, this is a new distribution, which is everything in here, every blue dot is a mean of sample size 25. And the means have a lower spread to them, i.e., tighter distribution, but they have the same mean on average. I hope I've always found this one that probably I taught this for a semester and didn't even understand it. I was like, what? Last question on the homework, then we'll do a little 320 right here. Okay, got enough time. Nice job, Nancy. It's tricky chapter. Truthfully, I'll say it's one of my lesser favorite chapters to teach. Lesser favorite chapters. I don't know. I have chapters I love. Confidence rules are amazing. We're about to do that soon. Okay, let's do it. You got a histogram right here. Describe the histogram. Monster Man. How's Monster Man feeling today? What shape is Monster Man feeling? Monster Man here. I got a Monster Man wrong like a week ago. Monster Man would be very sad about that. How's this Monster Man feeling? Right skew, left skew, unimodal, symmetric. What's going on? Well, it is unimodal. It's unimodal because of this. You can be unimodal and skewed. Skewed to the right to the high, left to the low, whatever way the Monster Man's tail goes. Right to the high. Explain how these simulations show you the central limit theorem. Here we go. And if you take a look, this is a very, very skewed distribution. It does appear to become more normal as n gets larger. This is the larger n. N is approaching a very large number. So the simulations do support what the central limit theorem says. The sample size increases the peak. Now the peak is the center. So the center is increasing, decreasing, or staying the same. When it says the peak, which is the center, is the center getting higher, lower, or staying the same? Because that's mu y bar. Mu y bar equals mu. So the center should do what? Theoretically, the center should do what? Get higher, get lower, get smaller, get tighter. What should the center do? What should the center do? Random numbers calling me. Well, the center is the mean, and via the equation of mu y bar equals mu, we know mu y bar equals mu. So if n gets larger, we were just talking about this a moment ago,
It doesn't matter.
doesn't matter because it's going to stay the same. So the answer is, on the example problems were similar compared to, kind of. The practice exam is really the best thing to look at. It's going to stay about the same. Questions like this, there's a lot like that. There's like, what changes about it? A lot of theoretical. The shape of the distribution does what? And don't click their answers. What does the central limit theorem say about the shape? The shape of the distribution is becoming more what? And you can see it if you go across them. The shape of the distribution is becoming more what? Here it is, here it is, here it is, here it is. The shape is becoming more what? As n increases, the distribution becomes tighter and more what? As n increases, the distribution becomes tighter and more what? The two things the central limit theorem says is it'll become tighter and more normal. And the tighter is that the variability will get what? Larger, smaller, or stay the same. Because variability is spread of a distribution. So the variability should increase, decrease, or stay the same. Variability is spread. Like, how variable is it? Like, does it have a lot of variation in it? So the variability should get larger, smaller, or stay the same if it's getting tighter. Because that's one of the two things. It'll get tighter. So that means the variability will what? Increase, decrease, stay the same. The variability will increase, decrease, stay the same. What do you think? What will the variability do? It'll do what? If it's getting tighter, that'd mean less variability. At least 30. Great job, Shane, right there. Good work. Is one of our rules that if you have 30, you're good? Yes or no in the chat. Is one of our rules. Jax, you might elaborate on that. I don't know about that note. You might be thinking large and offend, but double check the note right there. Is one of our rules that if you have 30, you're good no matter what? Is that a rule of thumb? Review 2? Is one of our rules that if you have 30, you're good no matter what? Yes or no in the chat. Is one of our rules, hey, if you got 30, you're good? Isn't it, if it's normal, we need a sample size of 1? If it's skewed, we need a sample size of 2? And if it's heavily skewed, we need a sample size of 100? And if it's super duper skewed, we need a sample size of even larger than that? Exactly, Sawyer knows there's no rule of at least 30, you're good. No. Since the distribution of means is heavily skewed, let's see right here. Since distribution of means is heavily skewed, it doesn't become less normal. It doesn't become less normal. That's wrong. A is just wrong. Since distribution of means for the simulated sample is approximate, no. Since distribution of means for the simulated becomes less skewed. No. Here's the answer. Since the distribution of means for the simulated samples of any size remains skewed, the rule of thumb does not hold. There's no rule of thumb like that. That's got it. So the large enough n consistent states, and I will say this, we did review this during office hours this morning. We did a full 1314 review this morning, so I would check this out. I might be thinking of another review thingy, but a distribution on a curve of, say, 95% is more sure, sometimes much wider. Yeah, you might be thinking of confidence rolls with 68, 95, 99.7. When you get more confident, the interval gets wider and wider. Jackson, good review. Or we're getting to that. That'll be confidence rolls. As when you become more confident, the interval gets wider. A 95% confidence interval is wider than a 68 and wider than a 95, but it's less precise because precision is how tight it is. Confidence and precision are inversely related. Let's do a little 320 review. Gonna clear my screen, do some 320 review. Okay, we probably have maybe a little more time for 201 with this. Might go on a quick walk. I feel like drinking a Red Bull today. I shouldn't. I brought all my Red Bulls, or some of them. Quick review. Okay. Here we are with some 320 review. And we got a lot of fun stuff right here. Okay. So for 320, we've been building regression models. White Monster later for White Monster's good stuff. Jackson, you got some good choices right there. I got some Kiwi Red Bull, I think. I think I'm gonna have one as a treat. I need it. I don't want it, I need it. So what we need to do first when we open up an R document, usually load our libraries. LIB is short for library, and you can just run that snippet right there. And we usually load in reg class, which is regression class, if it wants to load. I've already loaded it in. It'll show some warning messages down there if you haven't. Next, we can go data and load in something like survey 10, survey 11, survey 09. This is not stat 201, but still, you might see some stat 201 topics here with regression. So hang out if you want. We're talking 320 right now. So this is students from year 2011, 14 years ago. And we can do things. We can do general regression right here. And we can predict someone's GPA. So we go in here and make a model and save into x07.gpa tilde. And let's predict their GPA using something like, what should we use? X what? You can yell at an X. I'll pick one in a second, but just say X something something. I'm going to attach it. Tell me X something something. You're like, oh, use X this. Predict their GPA with X41, X whatever. You can just pick one if you want. What would we pick? Let's say... Ooh, how smart you think you are. So there's the model. And here's the regression, which we've covered in 201. So we can visualize it pretty quickly. And there's the visualization of the model. And so this is people who think they're smarter do have higher GPAs typically. There are big outliers down here. People who are far away from the model. It's actually not a bad model. We actually did pretty good on this. And then we get the coefficients in here. A little bit of a long output. And there we go. Someone who thinks they are smarter than no one is predicted to have a GPA of 3.03. For each additional percent you think you're smarter than someone, we expect your GPA to be 0.0046 higher. So two people, can't even do 320 interpretations right now. Two people who differ in their percent more intelligent than they think other people they are expected to differ in their GPA by 0.0046. But the person who thinks they're more intelligent is expected to have a 0.0046 higher GPA. And we would say only about 5%. I'm looking at the R squared down here, and this is for 201. Blank percent of the variation in Y is explained by the variation in X. About 5% of the variation in somebody's GPA is explained by how smart they think they are. And we see here the residual standard error, which would say that when we predict someone's GPA, we're typically off by 0.0454. Now, here's where we go beyond 201, and we've been doing things like this, where we can go in here and we can add also in this someone's, let's go favorite alcohol. So if we go down here to favorite alcohol, which I saw just a moment ago. Where is it? Favorite alcohol, X40. And we run it now. We can visualize the model here. We should have put a none on here. I don't know why there's not a none. Oof. Beer. We could also do an interaction on this if we wanted. Oops, I did it wrong. Oh no, I broke it. Weak interaction. Weak interaction for those who know interactions. That is a weak interaction. Okay. And it looks to me like it is significant. Oh yeah, it's significant. Oh yeah, that's significant. So when we have this right here, we see that people predicted at the highest GPA actually don't drink. We did put none on here. People predicted at the lowest GPA are drinking beer. There you go. Not that you must. I mean, that person up there has got like a 4.0 almost. They're way up on the scale. I think the graphic doesn't even go that high. But person down here, you say, oh, I shouldn't drink, and not doing that well, but you're not drinking. And so we see the coefficients over here of differences. And all of these are compared to beer because beer is the reference level. And you can see the coefficients of the indicator variables right there. So, yeah, which one should we do? We got just enough time. So that's a little bit on 320 right there. Which one should we do from the quiz, Jordan? Let me pull up a quiz question. They're very similar to the homework. I need that Red Bull. All that sugar. All those crazy things in there. I got like 7.5 hours of sleep last night. Is this the quiz? Well, we've done this one. A histogram to the right? We did that one. That one's the exact same. That's literally the same question. Histogram to the right. Let's do it. Okay. Oh, this is question 7. We'll do it. This is question 7 from the homework 2. We'll do it here. Good question, Jordan. And a lot of the ones are kind of repeat homework questions. Like they didn't have that many for this. Here we go. Stat 201. Thank you, Jordan, for asking. Chapter 14 quiz. And the histogram to the right. So when you look at this histogram to the right, what kind of monster man are we looking at here? What kind of monster man is this? What kind of monster man are we looking at here? What kind of monster man is this? You know monster man, right to the high, left to the low, whatever way the monster man's tail goes. Yeah, it's fine. We'll finish this one off real quick. What kind of monster man are we looking at here? Very important we know right to the high, left to the low, whatever way the monster man's tail goes. We have to know monster man. One of the first things we learn is skewness. What kind of monster man are we looking at here? Right to the high, left to the low, whatever way the monster man's tail goes. So the monster man's tail goes to the what side? What do you think? Right to the high, left to the low. It's a right skewed monster man right there. If I ever saw one, he lost his tooth. There we go. Monster man. Thank you, monster man. Okay. We got a right skewed monster man. Explain how these distributions show us the central limit theorem. The simulations support the central limit theorem. The mean of these distributions, is it getting higher, lower, or staying the same? Because very importantly, what do we know about the mean? We'll answer all three of these on this sheet right here. Mu y bar equals mu. So as we go to bigger n's, what happens to the mean? as we go to bigger n's, does the mean increase, decrease, or stay the same? So you just have to look at the equation. So as we go to bigger n's, what happens to the mean? The mean's about here. The mean's about there. The mean's about there. No, don't do that. The mean's about there. The mean does what? The mean gets higher, lower, stays the same. What does the mean do? Higher, lower, stays the same. What do you think? You have to look at the equation. Well, so n is what's changing about these. We can solve for the mean. Well, this is the mean we solve for by it's the mean. So what happens to mu y bar as n increases? That's not n, though. So what do you think, Jordan? It gets higher, lower, stays the same. Mu y bar will get higher, lower, it will increase, decrease, stay the same. We just look at the equation and think we would be plugging n in, but there's no n in this equation. Take a guess. Don't worry about being wrong. There's no n in the equation, so Rock knows.
It doesn't matter.
So do you think the mean will get higher, lower, stay the same? Nice job, Jordan. You got it. Yep, it's not going to change. It stays the same. What about the shape of these? They're becoming more what? The central limit theorem says that these will become more what? And you start to see it, especially right there. The shape of these will start to become what? They'll become less normal, more normal, stay the same. As n increases, the shape of the distribution, according to the central limit theorem, which is one of the two things it says, the shape of the distribution will become more what? Well, I kind of said it. Wait for Jordan to say it in the chat. So the two things the central limit theorem says is as n increases, the shape of the distribution becomes more normal. More normal. And you can really see it down there where it's like starting to really get like unimodal symmetric. And then the last thing is that the variability will start to do what? The variability will start to what? You can see it down here a bit. You can really tell down there. The variability will start to what? This is the variability. The variability is the standard deviation, which is how spread out things are. You can really tell it if you compare like these two right here. If you compare this scale to this scale, you can see the variability is getting much wider. And that's found by doing the equation of the standard deviation is equal to sigma over square root of n. So if n gets bigger, the standard deviation gets wider. If n gets bigger, the standard deviation gets wider, which means tighter. Standard deviation gets smaller. So we'd go right here. Oh, wait. Look at that, I'm misclicking. The peak of the histogram stays about the same because the mean doesn't change. And the distribution becomes more normal. And the variability decreases. And there is no rule of thumb of at least 30. You need 1 for normal data, 25 for skewed data, and 100 for very skewed data. So since the distribution still remains skewed, the rule of thumb is not really a rule of thumb. And we did this one. This one's virtually identical to the one we did. And we did this one. So we've actually done, all the variations have been done. Like they just changed the numbers. So if you basically do the homework, the quiz has nearly identical questions. Does that make sense? Like the grocery store one is just an identical version. So like the grocery store right here is just like the store's revenue. Here, I'll do grocery store really quick. Put on another one. I'm gonna drink a Red Bull then. Oh man, I'm like I shouldn't drink that much sugar. I shouldn't drink that much sugar. Should have got my 0 sugar Red Bulls. That's what I get for buying Red Bull and then being like, I don't want to drink sugar. Why'd you buy Red Bull? The grocery store's receipts. Show. Okay. So we're gonna do this one pretty quickly here. Let's see it. First thing you do is you mark your notation. We have right here the mu is equal to 30, the standard deviation is equal to 17, and they have 296 customers. So then this is just like the, please watch the weighted rates, just one where I go more slowly because all they're doing is changing the numbers in the context. all you would do is divide this to find out how much average they need to make on each customer, which is 31.756 on average. We're going to take the 30, which is the mean of the distribution, and the standard deviation is 17. We need to get the new standard deviation, which is 17 divided by square root of 296. And it's going to be basically 1, apparently. And very similar to our last one. So now we go back to the applet, which MuBot has the applet pinned. And we put in the new standard deviation. Very similar. And then the mean right there. Now we take and we get the observation they want to see. They want to make at least $9,400 off the 296 customers, which means they need to average this. So they want to see at least that. So we say find the probability above this. And there it is right there to 4 decimals. And 4 decimals. The store takes in at most this on the worst 10% of weeks. So we go back to the applet and we go down here to the worst 10%, which means we need to enter in a area and need to go to the far side of the curve over there. And then we're going to times that by the 296, which is the amount of customers. This is what the average per customer. And then we go back here and drop it in. And then we round to 2 decimals and we get it right, hopefully. Got it right. Once again, it's just the weighted waitress problem with different context. So it's the exact same steps to solve it. But yeah, that basically does them all. We've kind of done them all. And might go for a quick walk. Any questions? Let me hit save on the notes. Really quick version of that. And oh, and I got to see Mike's video of it. My first pitch. Until then, I'm going to head off, go for a walk. Bye for now, everyone. Bye.